Welcome to Chapter 5, everyone. Chapter 5 is all about introducing the integral and exactly what all of that means. And we're going to start with some sort of background stuff and do an integral sort of, remember when we did the derivative, we had to do it the hard way first, and then we had the easy way. So we're going to get a better understanding of where all this comes from. And it all started with Sir Isaac Newton, and he had a question about a velocity curve. So we'll say in a velocity curve, is the displacement of a moving object. And this is the area under the curve. Do you remember back in the day, rate times time is distance? Well, here's the rate and here's the time. And when you multiply two things together, you get area. So that is going to form, and if it's a constant 60 miles per hour, which in real life, of course, no one is going consistently anything ever, certainly not driving or in any velocity that you and I are familiar with. So if we do here, then what we have is this area, and we've gone for 2 hours. So how far did we go? Well, we know how to find the area of a rectangle. So the distance after 2 hours is 60 miles an hour rate times time, 2 hours, is our distance, which is going to be 120 miles, which corresponds to the area under the curve here. So we're now going to focus on the area under the curve and what it represents. It's not always going to be velocity and things like that. We're going to have some more abstract reasoning and so on. But one of the important things that we're going to need to be able to do for this chapter, for this section, I should say, is have a curve. So we have t squared. Here we have a parabola. So the velocity curve is v of t equals t squared. And t is going to go from 0 to 8. And what we're going to do is we are going to partition this into two partitions. That's when n equals 2. And what we have now is we have this area here, and we have this area here. Now, what we're going to eventually be doing is creating rectangles to try to approximate the area. But right now, we're just talking about partitioning. So here we're breaking this into two separate groups. Here, when n equals 4, we're going to partition it even further. So we're going to break this up into 6 and 2. And then we're going to partition it into 4 regions. So now we have region 1, 2, 3, and 4. So we have this area here. We have this area here. This area here. And we can see this last one is going to have the majority of the area as we're looking at that. But you could see we could partition it even further. And these values down here, you will hear me refer to them as node points, or partition numbers. So a couple of different ways to go with that. So here's the basic idea of what we're going to be looking at in this section. And we'll get into the nitty-gritty here in just a couple of minutes. So the idea is we want to break up, and here are our partitions. They're all broken down, our node points. And eventually, we're going to want n to go to infinity. That'll give us the exact area, but we're not there yet. So we're just going to do some approximations. Now, the distance from partition to partition is called delta x. That's in the previous chapters, we called that h, but now we're going to call it delta x. Delta is a capital Greek letter D. You can kind of see where we get our D from. And the D stands for difference. So this is the difference between this node and this node is going to be delta X. And that's going to be consistent all the way across. Now, just a little spoiler alert, delta X eventually becomes our dx. If you remember in the last section of chapter 4, where we had a dx with our integral. Now, we have these points in between our nodes, and you can see that the dotted line is representing that. They don't necessarily, now this has X bar, which implies that it's the average of the two. We'll get to that. We'll get to the average, but right now it's just anyone that's between. And often we refer to the area under the curve under the curve. And that's going to be delta X, which we'll talk about. Actually, the way you find delta X is going to be B minus A. Those are the endpoints. Here's B and here's A, divided by N. That's the number of partitions that are being asked for. So this is going to be, and instead of the bar, I'm going to write a little star next to them. This is going to be times alpha X sub 1 star plus delta X F sub 2 star plus, and I'll do one more, delta X F sub 3 star plus, and this is going to go all the way until we hit plus delta X F sub N star. And this is referred to as a Riemann sum, named after a mathematician. This is a Riemann sum on A to B, starting with A, ending with B. Now, there's a couple of different rectangles that we can do. We can have a left Riemann sum, meaning we're using the f of x is going to be the left part of it. And you can see in this case, we're getting a little too much. Now over here, we're missing some area. You can see this little tiny. Here we have too much. Here we have too little, too little, too little, too little, and not too much. And you can see that this is going to be a problem. Same with the right Riemann sum. We're going to run into where we're using the right side. So notice here we start with A as a height, f of A as the height. And again, the length here is the delta x. Now for this one, we start with x sub 1. So we're doing our right bar that we start. So this one we start with A, this one we don't. We start with the x sub 1. And we go over here. And again, you see we have too little area, too much, too much, too much, too little. And we're going to run into these problems. Now, what we can do is come up with the midpoint, meaning we have A and then we have x sub 1, and then we find the exact midpoint. And you can see just barely on this part of the rectangle, we have a little too little area, and this one a little too much. And you can see the hope is if we hit in the middle, we're going to get a little too much, a little too little, and hopefully it'll average itself out. And now we're going to get to the nitty-gritty here. So we're going to do the same Riemann sum, except we're going to do the left Riemann sum with n equals 6. We're going to do the right Riemann sum with n equals 6, and then we're going to do the midpoint. And although I'm not going to do every single calculation, what you'll need to do with your calculator before we do anything, because we're talking about sine of x, is you will need to make sure that your mode is in radian mode. If you're in degree mode, what we're about to do will not work. And I would recommend those of you watching this video that you actually pull out your calculator and do the calculations. Pause the video whenever you need to pause it, but actually do it yourself so you get the practice. All right, let's start with our left Riemann sum of f of x equals sine x. Now I'm going to type in sine x here, and I'm hoping that'll make things a little bit easier as we start doing this. So let's start with our delta x. Delta x, this will be the same for all of them. This is b minus a, so here's a and here's b. This is pi over 2 minus 0 over 6. This is going to be pi over 12. So this will be consistent for all three of these examples. All right, so let's get into it. First off, we need to partition them off. And because we're doing a left Riemann sum, this one here is going to be 0. Then we have each of our partitions. And here we're going to start at 0, right, 0. Then I'm going to add a pi over 12, then add a pi over 12, then add a pi over 12. And although I can reduce some of these, I'm just going to leave them over 12. It really makes it a lot easier for us to try to kind of visualize what it is that we're looking at. And because we're doing the left Riemann sum, our rectangles are going to be here. And so when we, and by the way, we have our delta x, that's the distance here. Now the height is going to be f of these, so it's going to be sine of that. So the left Riemann sum is going to be delta x. Let's write it out like this first. Delta x f of 0 plus delta x, which we know is pi over 12. F of pi over 12 plus delta x f of 2 pi over 12 and I want to point out the last height that we have is the delta x f of 5 pi over 12. Please note that we are not using pi over 2 as a height. You can see there's no rectangle that goes that high. For the left-hand side, right-hand side, there will be. So let's rewrite this. I'm going to factor out a delta x and write it as pi over 12. And this is going to be the sine of 0 plus the sine pi over 12 plus the sine 2 pi over 12 all the way up until we have the sine 5 pi over 12. And again, you need to make sure that your calculator is in radian mode. I can't emphasize that enough. And we'll close there. And when we do all of this, I've pre-worked this out. This becomes 0.863 about. Please double check my numbers. I'm going to encourage you to do so. One of them, I'm going to write everything out coming up, but I don't want to waste too much of the video doing that. Let's do this again, but with the right Riemann sum. And what does that mean for us? That means that we are going to be starting so the right Riemann sum, and once again, to label these, this is 0 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, and then 6 pi over 12, of course, is pi over 2. And now what's different about this one, which is going to be definitely in contrast to the picture we just did, is our rectangles are now this way. And you can see for this one, we're definitely going to be undershooting that area. We have all this empty space that we're missing out on. Here, we're overshooting it for sure. So what value we get for this one is definitely going to be too large. And let's do the right Riemann sum. And this is going to be pi over 12 times the sine of pi over 12. And I'm going to factor out like I did up here. So this is going to be the sine pi over 12. Now notice that's different than when we started with the 0 here. Here we're starting with the pi over 12. And we're going to go all the way to pi over 2 in this case. And notice we didn't do the pi over 2 for this one. Notice they end differently. They also start differently. So for this one, again, we're going to overshoot this. And again, I worked this one out earlier, and you can certainly verify this. And you can see this is definitely larger. Now, a common practice is to find the average of these two, add them up and divide by 2, which will give us probably a better approximation since we have too little here and too much here. But let's do this one more time, but with the midpoint. So we're going to split this up with our same node points here. So we have, once again, 0, pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12. However, I now need to find each of the midpoints. How do I find the midpoints? So meaning exactly in the middle here. So what I'm going to do is I'm going to add up pi over 12 plus 0 divided by 2, and that's going to give me pi over 24. And each of these midpoints, this is 3 pi over 24, 5 pi over 24, 7 pi over 24, 9 pi over 24, 11 pi over 24. And what we're doing with that is our rectangles are now going to go to here. So you can see we're getting a little too much and a little not enough of each of these heights. So this is going to be a little bit different as well when we're adding up our stuff. So here's the midpoint Riemann sum. This is going to be delta x once again, same pi over 12. That doesn't change. This is now going to be the sine pi over 24 plus the sine 3 pi over 24. And so on, plus the sine of 11 pi over 24. And when we add all that up, once again, please verify this. And you can see that is definitely between here and here. So our midpoint Riemann sum is going to be a lot better for us as far as accuracy goes, but you can still see it's not perfect. And eventually we will get to perfect, not in this particular lecture, but later in chapter 5. All right, let us move on to sigma notation. All right. So first of all, this is sigma notation. And what this means is of k. What this means is I'm going to have k equal 1 plus k equal 2 plus k equal 3 plus k equal 4 plus k equal 5, 6, 7, 8, 9, all the way up to 10 is what this means. The summation notation or sigma notation. Most teachers teach it both ways. And I'm not going to give 3 examples. I'm just going to give a few. Another example. So this would be 1 squared plus 2 squared plus 3 squared, and so on. So some properties to note. So if I have a constant times a function of k, and I did this already with the delta x, we actually can take that c out. And if we are adding or subtracting, this can be broken up into 2 separate, which we will definitely do today. And I could give more examples, but we're going to see plenty. We have some very specific rules, and these are very, very important that we're going to be using. When we have a constant, what we're going to do is we're going to add up that constant n times. So this is going to be c plus c plus c plus c, a total of n times, which is going to give us c times n. Now, these next 3 are going to be very important for today's lesson. I'm not going to derive where they come from. They can get quite complicated, actually. But these are going to be ones that you're going to want either to memorize or put on your note card, depending on what your teacher allows you to do. So adding up 1 plus 2 plus 3 plus 4, kind of like I did up here, it is going to be 1/2 times n plus 1. The k squared is going to be 1/6 times n times n plus 1 times 2n plus 1. And k cubed, and we're going to use all these today, is going to be this one squared. So I will refer back to these as we continue to use them. And there's only one of them that I'm going to full on write out. And the other ones, we're just going to sort of derive them, and then I'll explore the answer for you. So this one here, we have x cubed plus 1. So 2 cubed is 8. 8 plus 1 is 9. So we're going to stop here. And the function looks like this. And we're going to be going from 0 to 2. We're going to start with the left Riemann sum. And let's start out with our delta x here. Let's push that up a little bit. Remember, is b minus a divided by n, when in this case is 50. 2 over 50 reduces to 1 over 25. Now that's going to be the base of each of these. So here we have 0. And then next up we have 1 over 125. 2 over 25, and so on. It's too small to draw the picture, especially certainly because we have 50 of them coming up. And even these distances are over exaggerated. Yeah. So here's what we're going to end up with. Our left points are going to be 0, 1 over 25, 2 over 25, 3 over 25, up to 49 over 25. Notice that's just shy of 2. That'd be like right here. Because they're left-hand points is the reasoning for that. And x is going to be, and this is going to be really important here, delta x, which we know is 1 over 25, times k minus 1, because we're starting at 0. So it's k minus 1, which in our case is going to be 1 over 25 times k minus 1. And this is where k is going to start with 1, 2, 3, 4, and so on, up until we hit 50. And you'll note 50 minus 1 is the 49 over 25. So everything jives up with that. So we are going to have our base times our height. And just to be clear, this is our base, and this is our height. So each one is going to be f of 1 over 25 times k minus 1 times delta x, which is 1 over 25 in this case. Again, as k goes from 1 to 50. So putting this in context, we're saying that the area under the curve is about summation k equals 1 to 50 of f of 1 over 25 times k minus 1 times delta x, which again is 1 over 25. And I'm going to use a rule, and 1 over 25 is c in this case. I'm going to pull that outside. It's just going to make things a lot easier. So this becomes 1 over 25 now f of 1 over 25 to k, that is going to be here. That's our function. Remember, this is x. X is that. X cubed plus 1. All right. I'm going to show this work this one time, and I'm not going to go too in depth with it. But I'm going to break this up into several pieces. Real quick, this is k cubed minus 3k squared plus 3k minus 1. All right. Now, 25 cubed is 15625. I will show you. 25 cubed, 15625, because that has to get cubed. So this becomes 1 over 25 times 1 over, and we just calculate that, 15625 times, now that's going to be the summation k cubed minus 1 over 25 times 1 over 15625 times 3 summation k equals 1 to 50 of k squared plus 1 over 25 times 1 over 15625 times 3 summation k equals 1 to 50 of k minus 1 over 25. No, I'm sorry, this becomes 1 over 25 times 1 over 15625 plus the 1, but the 1 also gets 1 over 25. That is crazy. So after, by the way, remember k cubed, so I can fit all of this on here, is there, where n is 50. So 1/2 50 times 51 squared is going to be what goes there. Summation of k squared is here. 1/6 times 50 times 51 times 101 is going to go here, times all those numbers. Summation of k is right here. 1/2 50 times 51 goes right there. Summation of a constant, so we can squeeze that in there. Right here, summation of a constant. Oh, I went too far. Summation of a constant is right here. That's just going to be c times n. So c is the constant 1 over 25, n in this case is 50. So it's going to be 50 times 125. And after doing all of that, we get that this is about 5.8416. Now, that may seem insane to you, and I'm not going to do that to you again, but I just wanted to show you the level of detail that is involved with this. So let's do the right Riemann sum for this one. And the right points are going to be, and once again, we're going to have our same graph. In this case, we're going to start at 125 and we're going to end at 2. So we're just slightly different from what we had above. And so the right points are going to be 1 over 25, 2 over 25, 3 over 25, up until 50 over 25, which is the 2. So notice we're starting just off and we're ending just off. Starting just a little bit different, ending just a little bit different. And that is going to give us, our x is going to be 1 over 25 times k. That's our x value, where k, once again, equals 1, 2, 3, 4, up to 50. Now, the previous one had the k minus 1. Once again, this is the height. Our base is the same, it's still 1 over 25. So our area is going to be the summation times 1 over 25, which for us is going to look like this: 1 over 25 of 1 over 25k cubed plus 1. And without writing the whole thing out again, like I did a few minutes ago, this becomes 6.1616. And you can see we could take the average of those two and get something a little bit better. But, you know, so let's do the midpoint now. Midpoint. Here we are. And once again, I'm going to over exaggerate this just because I want us to be able to see what it is that we have here. So here's 0. And here is and again, I'm going to over exaggerate. This is 1 over 25, 2 over 25, and in between those two, so if I take 1 divided by 25 plus 0 equals divided by 2, convert to a fraction. This new midpoint is going to be 1 over 50 to 3 over 50, and so on. And I'm obviously way over exaggerating with the picture. So to find that midpoint, I'm going to take the left point, which was 1 over 25 k minus 1, and the right point, which was 1 over 25 times k, and we're going to find the average. This is going to be 1/2 times 1 over 25 k minus 1 plus 1 over 25 k. And I'm going to factor out a 1 over 25, so that's going to be a 1 over 50. And we are left with k minus 1 plus k, which is 1 over 50, 2k minus 1. All right. And then we could do the summation of all those. I'm not going to go through all that again. The reason I don't mind skipping showing all that work, although you may need to do all that work kind of like I showed you before, after we finish chapter 5.1, we have a better way of doing this. All right, so let's summarize everything real quick. So our left point is delta x times k minus 1 plus a, whatever a is. A has been 0 for our problem, so we've been ignoring that, but it needs to be plus a. The right point is going to be delta x times k, again, plus a. And for the midpoint, it's going to be delta x. And actually, what I could do is factor out a 2, and that'll give us 1 over 25 k minus 1/2. And that tends to be the way that we write this. K minus 1/2. And the reason is because we can clearly see our delta x is there, like we had there. So up here, what I did was I factored out a 2, reduced it, and we ended up with that. This is, again, plus a, and this is all k equals 1, 2, 3 until n. Now that was an abstract, bizarre lesson. So we'll see where we go from here.